Hey, so welcome back. Today is a slightly different kind of video, but something interesting I find nonetheless. So many of you may have seen Ben Eater's video on this, which is where he took this program, this Fibonacci program in C, and showed its disassembly, and then went over the disassembly and showed you where certain functions were. Well, I have this program compiled down to here. This here is the 8080 assembly listing compiled by Aztec C for the 8080. And as you can see, it is much different than the disassembly that Ben Eater was working with. And that's because, well, he was working with a modern processor. And I'm not. I'm using an 8-bit processor with only, 8 registers? A, B, C, D, E, F, and H, L. So I guess that's not. But yeah, those are the only ones. The F register is actually a flag register. Remember that. So it's A, F, not just A. Anyway, let's take a look. This is very interesting. So first we have int main, and this is just scoped out. So we have the first entry point, the last entry point. Note that main is type int, so it must return a 0, or at least an integer. Here it returns a 0. Now let's look here. So we have main. These things up here, these externs, are part of the c.lib part that you link up with for the Aztec C compiler. I'm not quite sure what these do. If anyone has any idea, please put it in the comment below. So it says call it zsave. I'm wondering if this is a stack or a register save, but I have no idea. Anyway, so it says, first it says LXI D 0.2, and 0.2 is way down here at the bottom. 0.2 is here. 0.2 equals -6. Now, what is this -6 here? Well, curious, because here we have 3 variables. We have 3 integers. We have x, y, and z. And another curious thing is if we look at the data types for Aztec C, we can see that an integer is 2 bytes long, and 3 variables, x, y, z times 2 is 6. So what this is doing is setting up, this is setting up your stack offset, because each one of these is 2 bytes. So that is why that is so. Anyway, as we move on, this is going to be very interesting. So first here, we have int x, y, z. That's what that line does. And now we have a label here, and the next thing we have down is the while loop. So naturally, this 3 would be the while 1. Now this is where things get absolutely bananas. So I load 1 to HL, so L is 1, H is 0, move 0, H, right, 0 is an H, move it to A, and then OR A with L. Well, what this does is this does 0 or 1, which equals 1. And it says JZ, jump of 0 to 4. And well, where is 0.4? Well, 0.4 is way down here. 0.4 is the end. 0.4 says LXI H0 and return. Well, what is the H0? LXI H0, this here is return 0. Because if you read the Aztec C manual, a 2-byte return is an HL, a single byte return is an A, and that's return. Now, this may be a little intriguing to you. Well, what is this doing? This here is testing if 1 fails. Now, normally you just have a jump loop, but because this is the Aztec C compiler and it's not horrifically smart, it has to test whether or not 1 will fail, and well, it never does. So now we can move on to the next part. So right after this JZ4 naturally is the x equals 0. Right here. And how does this work? Well, it looks complicated. It looks very complicated, but it's not magic. All it does is it loads 0 into HL, and it does exchange. In exchange, what exchange does is it takes HL and it swaps it with DE. So now the 0 is now 0. And then it says, this is the fun part, HL oxide H 6 minus 0.2. And remember, 0.2 is -6. This is the fun part. Whenever you see this offset, 6 minus -2, this points to x. Because we have 3 variables, x, y, and z, it's safe to assume that 6 minus 0.2 is x, 4 minus 0.2 is y, and then if we go even further down, 2 minus 0.2 points to z. So there we go. So we have DE loaded to 0. We have x, the location of x in H, add to the stack pointer. So the stack pointer now points to where x is. Move, this here is move low byte to x. Then you increment, right? HL plus, move high byte to x, and done. That is what this is. X equals 0 is this block. It is this right here. Then, if you look here, there's another block. This is y equals 1. And it does the exact same thing, but with 1 in HL. And it does the same exact loop. Okay, so let's look at our C code. So we have x equals 0, y equals 1, and then we have the start of a do loop. Okay, do while. So let's hear. So here is 0.7. This is safe to assume it is the start of the do. And before we move on, let us solve this do loop, do while first. So it says do while x is less than 255. Well, so this is all the code inside the do while, everything, until we get down to here. Well, this is interesting. It says here x, so we are grabbing x right here. Okay, well, that's interesting because right here we need to grab x. Then you move you move x to DE. So this here, right, is move x below high to DE. Okay. And then I load, oh, that's interesting. That's 255. Look at that. We have a 255 right here. Let's load 255 to HL. And then, interestingly, it calls .lt. Well, there is no LT in this code. This must be part of the c.lib library, and it does less than. And what it must do is it must do DE less than HL and then set Z flag. So that's what it must do, because down here, jump not 0 to 7, which is the start of our do loop. So we have solved the do while. So down here is the while x less than 255. Cool. So we're making some good progress here. So oh no, what is this? This is a printf. Oh man, printf. We all hate printfs in assembly because printfs does not. No one writes printfs in assembly anymore. You all use libraries. So we can expect to use a library call. And as you can see, there's a library call right here, printf. But right here, let's just go down the column here. So this is grabbing x, right? Okay, so we grab x, but wait, hang on. We grab x, we move the low byte to E, we move the high byte to D, but then it says push D, so push x val, or this would be x asterisk, to stack. So so this is grab x, but this is, remember, this is ampersand x, right? This is the location of x. This is the actual value, and I want to push it to the stack. Then LXI h 0.1 plus 0. Now, I'm not really sure what this 0.0 is. This might just be, a default offset somewhere in the library. Now, what is 0.1? Well, if you look here, this is 0.1 dB, 37, 110, 0. And this, you must be thinking, well, what is this random code? Well, if you know ASCII very well, you may recognize that 37 is %, 100 is lowercase d, and then 10 is carriage return. Or what is it? 10 is new line or carriage return. I cannot remember. And then you have a string terminator. And that is very well and good, because right here we have exactly that. And remember, for a string, the string termination character is implied. So we have, let's keep bumping you. We have x. We have get string. So we have the location of the string. We have x all pushed to stack, and you're ready to call printf. So then right here is printf set sign d n x. And this, I think, is just cleaning up, these two pops, I think, are just cleaning up whatever printf did. You take the last two, so these two, you take the string address and then the value of x, and you don't need them anymore, so you just pop them off the stack, just pop them to D. You're going to overwrite D next anyway. So we have printf Done. Now, what is this? We have z equals x plus y, x equals y, y equals z, and this is where things get a little tedious. But it should be okay nonetheless. Break apart z equals x plus y. Well, what you have to do is first you have to take x, you have to get y, and then you have to add them together, and then you have to store to z. Well, let's do it. So here we are. This is going to be z equals x plus y. Right, okay, so then here we're grabbing x. Right? Because that's the 6 minus 0.2. Right, okay, move m to e, m to d. So this here is x is now in dE. Okay, well this is grab y, right? Okay, so grab y, 4 minus 0.2. Let's see here, move m to a. Okay, so this is interesting. So low byte y goes to a. Interesting. Okay, move up, and then the high byte goes to h. So then high byte y goes to h. And then move a to l, so then y is now in hl. Okay, so we have x is in dE. Okay, we have y in hl. So then just do a double add for d. So this is add dE, which is x, to y, and then exchange, flips hl and dE. So then hl equals, hl, just literally hl equals z value. And then we are grabbing z. Let's move. Sorry. Oh my gosh, this is so confusing. dE. Because remember that the value of dad, double add, goes to hl. And then when you swap it, hl goes to dE. So this is what it's saying. So this is going to be the location of z. Store the low byte to m, store the low byte to h. Sorry, yeah, so store the low byte to that location, and then store the high byte to that location. So this is store z val to your location of z. That's what this block does. And it says LXI h4 minus 0.2. Well, that must be x equals y, because this grabs y, right? So grab y, okay. So at location, so then right here, so y is now in dE, because you take m, which is the value at hl, put it to e, increment your pointer, take the value at hl, put it to d, so y is now in dE. So then here is grabbing x. As you can see, it's pretty easy to run through now. So hl is now at stack pointer location x. So then this, where you take e, move to m, d, move to m, Well, y is in that. So this is move y to, oh my god, there we go, x. This right here is x equals y. Okay, we are almost done. And what is that final thing? That final line here is y equals 1. Sorry, the final thing is not y equals 1. Down here, y equals z. So we have to grab z and then move to y. Well, what is this right here? We have y equals z. Grab the location, oh my god, location of z. And then m to e, increment h, m to d. So then z is now in d, e. And here, this is grab x, right? Okay, move e to m, increment h, move d to m. So this is store d, e, which is z, to location x. And that is it. We have taken this C program, okay, compiled it using Aztec C Compiler, and then turned it into this assembly. And we have deconstructed this assembly code to see exactly what corresponds to what with this. If you are wondering why this assembly listing is so long compared to the one Ben Eater did, just remember that each one of these registers, D, so it's A, B, C, D, E, H, and L, are all 8 bits wide. But you can double them up like this to be B, C, D, E, and H, L. And these are each 16 bits. And remember, 16 bits is the length of an integer. 16 bits is 2 bytes. So it's the length of an integer in Aztec C. I'm sure that if I did long x, y, z, it would be a somewhat different listing. So yeah, there we go. That's what I wanted to show you today. Something a little different. And I hope this will demystify a lot of AG80 and Z80 assembly programs for you. They can look pretty magic with their very rudimentary instruction set. But if you break it down line by line and go slow, you can and you will figure out how everything works. Thanks, and I'll see you in the next one.